Right, and it's also the last topic. This lecture 24 is also the last topic that we'll be talking about fluids, fluid dynamics. We'll move on to temperature and heat in the next lecture. Um, but so far, what we've learned about fluids is we started this topic by defining the properties that describe fluids, density and pressure. And then we looked at buoyancy as the consequence of pressure increasing with depth. But in both lectures that we've had so far, we assumed that the fluid was static, meaning it was not flowing, right? It's just stationary. But in reality, fluids flow. And so today we will look at fluid dynamics, how to describe a flowing fluid in terms of continuity equation, and Bernoulli's equation relates pressure, velocity, and height in a flowing fluid. All right, so yeah, when fluid flow is quite important. As I said, in reality, fluids flow, and these are just some of the applications where fluid flow is important. And so when fluid flows, we're sort of looking at how much fluid is crossing per cross-sectional area, and we define this as the volume flow rate, or simply flow rate. Okay, so when we say flow rate, it's how much fluid is crossing an area at a given time. When we say how much, it's the volume. Right, so we use the symbol Q to designate flow rates, and by definition, therefore, flow rate being the volume of water crossing an area per unit time is then defined by this mathematical equation Q equals V over T. So if we're looking at a pipe with cross-sectional area A and fluid is flowing through this cross-sectional area A, flow rate Q is of course defined as volume over time, but volume is just measure of 3 dimensions, right? So if you have area and you measure, for example, the distance over which the fluid travels at a certain time, then you can write volume as the area times the distance, right? So volume can be measured as the cross-sectional area times length being the distance for which the fluid traveled for a certain time t, and we learned that distance divided by time, that is equal to speed. So flow rates, aside from being defined as volume divided by time, can also be defined as the area, cross-sectional area times the speed of the fluid. So you can also think of flow rate as how fast the fluid is moving through a cross-sectional area A. Right. So two equivalent definitions for flow rates: how much, or the volume of fluid per unit time, or how fast the fluid is crossing a cross-sectional area A. Okay, sometimes when fluid flows through a pipe or a column, the thickness of the pipe doesn't remain the same. So here is an example of a pipe with uneven thickness. So fluids enters the pipe with a larger cross-sectional area A, and then at some point it encounters a smaller cross-sectional area A as the pipe narrows. Assuming that fluid is, not added or removed within the pipe, meaning whatever volume of fluid entered one end of the pipe should be the same amount, same volume of fluid that will exit the pipe, right? Assuming that no fluid is added or being taken away along the length of the pipe. So in which case, we have what we call the continuity equation, which says that the flow rate through area A2 should be the same as the flow rate through area A1. If you think about flow rate, the definition of flow rate as the volume of water, crossing this area A2, then it sort of makes sense, right? This, if, for example, you have 1 liter of water entering area A2, 1 liter of water should also exit the smaller area A1. Yeah, so that's the essence of continuity equation. The flow rates of fluid should be the same regardless of whether the pipe or the column narrows or widens. And in terms of defining flow rates as the speeds, flow rates flow rate out of area A1 should be equal to the flow rate out of area A2, and we get this relationship that the narrower the constriction or the smaller the area, cross-sectional area is, the faster the fluid should flow through it. And that's a consequence of this continuity equation relationship here. Okay, to visualize this, let's just try to visualize this to understand continuity equation, right? So let's assume here 1 liter of water is entering area A2. Let's just assume for a bit that 1 liter of water is equivalent to 1,000 sheep, okay? 1,000 heads of sheep. Continuity equation says that 1,000 heads of sheep entering A2 should also be 1,000 sheep exiting area A1. But A1 is a narrower gate. A2 is a wider gate. So if 1,000 sheep needs to exit A2 in 1 second versus 1,000 sheep needing to exit the narrower gate in 1 second, the sheep exiting the narrower gate need to move faster, don't they? Right? And 1,000 sheep who need to exit this wider gate, they can take their time and walk slower because we know that 1,000 sheep can easily pass through this wider gate, whereas 1,000 sheep passing through this narrower gate need to move faster. Does that make sense? Right? Yeah, and so continuity equation therefore says that the smaller the cross-sectional area, the faster the fluid needs to flow. Of course, then the wider the cross-sectional area, the slower the flow of fluid. So some phenomena, some examples, practical examples of continuity equation, if you ever tried to use a garden hose, here water flowing through the usual opening of the hose. If you try to put your thumb and constrict the area of the hose, you notice that water sort of flows faster. Okay, so narrower area here results to faster fluid flow. Right. Have you ever been to Hookah Falls? Oh, I mean, it's a magnificent view. If you have the chance, you should go and to appreciate. Yeah, you will really appreciate what's in this picture here if you see Hookah Falls. So at some point, water is flowing here. Notice how this is, a wider area here where water is flowing. And at some point, before the falls, before the elevation changes, the channel narrows around here. And if you've ever seen, if in real life, you really appreciate how the water really flows faster in this narrower channel compared to the wider channel. And that is again a consequence of continuity equation. The wider the cross-sectional area, the slower the fluid flow. The narrower the cross-sectional area, the faster the fluid flow. Right, clear enough? Okay, good. So let's So here, notice also in the Hookah Falls example, we can see a clear difference for how the water looks like on the surface. In the wider part where the water is moving slower, the water appears calm. And when the water encounters this narrower channel and it's moving faster, notice how it appears more turbulent. So we can classify fluid flow into two depending on how the fluid, how orderly the fluid flows. Classify flow as laminar or turbulent. Okay, when we say laminar flow, this is when the fluid flows in an orderly manner, and that occurs when the fluid is moving at a slower speed. Yeah, in the wider part of Hookah Falls, you'll see laminar flow, and as fluid flows faster, it becomes more turbulent. Okay. And that's when the fluid tries to move faster. And you can think of it as the, say, water molecules trying to move fast, and they want to move faster, so they're panicking and they're not orderly. Usually when we panic, we don't know what we're doing, right? And we sort of move about randomly. And it's the same thing with the fluids. So the molecules move randomly and they create this turbulent flow. And that happens when they're moving faster. Right? You can also observe laminar and turbulent flow in this picture of the smoke rising up. In the beginning, you have here this orderly flow of smoke, and then it becomes turbulent. Okay, around this area. Cool. Right, so let's just look at this example, a numerical example demonstrating continuity equation. So water pipe carries 1,000 liters of water, and the water is flowing per minute. 1,000 liters of water is flowing per minute in this section here at the speed of 2 meters per second. And then the pipe narrows at some point in this section here. You have a smaller cross-sectional area. We want to find first the flow rates in this section, in section A. And hence determine the cross-sectional area of the narrower section. And when the pipe narrows, what we want to find is the radius of the pipe. Yeah, the radius of the pipe narrows to 0.46 meters, and we want to calculate the new speed of water in that narrower section. Okay, so same question here, flow rate. So flow rate, we have two equivalent definitions for flow rate, right? It's the volume of fluids per time, or how fast the fluid is crossing an area A. What we know is the volume. 1,000 liters is, of course, volume. Time, yeah, 1 minute. We don't really know, although we know the speed, we don't really know the area. Okay, so to find the flow rates, we need to use the volume per time. Volume is liters, so we have to convert that. Yeah, volume is 1,000 liters flowing every minute, so we need to convert our non-SI unit. So liters to meters, again, that conversion factor there, converting liters to cubic meters, and of course, time to seconds. That should give you the correct unit for flow rate, meter cube per second. Right? Cool, simple enough. Okay, next question, cross-sectional area of the pipe. So cross-sectional area, that comes into the definition of flow rates. We've already solved the flow rate from before, and we are given the speeds for which the fluid is flowing, so we can calculate the area in meters squared. Okay. And once you know the area, you can then calculate the radius of the pipe, right? The pipe is a cylinder, so the cross-sectional area of a circle area is pi r squared, so you can find the radius by rearranging this equation here for the radius. Okay. Right. Still simple enough, right? Okay, then if the radius of the pipe narrows to 0.46 meters, so the radius you had in the wider pipe was 0.0515. Now it narrows to this should be 0.046 meters. Calculate the new speed of the water. Okay, so from the new radius, you can calculate the new area, and you want to calculate the new area because continuity equation relates the speeds at different areas. Old area and old speed refers to the wider pipe. Then new area, new speed, of course, refers to the narrower pipe, where after the speed in the narrower pipe, right? The old area, we've calculated that from before. Sorry about the typo here. That's an exponent of -3. The old speed is given in the problem in the wider pipe. Yeah, you can calculate the new area from the new radius. That gives you a faster speed, which makes sense, right? So in the wider part, you have 2 meters per second of speed. In the narrower part, your speed should be faster or bigger. Yeah.
Why couldn't you just do the flow rate divided by the new area? This isn't as well.
Yes, you can as well, because this is essentially flow rate. You're right. Yeah, that's probably a faster way because you save one step. Good. Cool. All right. That sounds simple enough, I hope. Yeah, I think, yeah, just understanding the continuity equation is the biggest thing, I suppose. All right. So what we've learned so far, we've now learned 2 things. Okay? We just learned that the flow, the speeds of fluid is affected by the cross-sectional area of the pipe or the column for which the fluid is flowing. The wider the area, the slower the speed. And we learned that the flow rate should be the same regardless of the area. We also learned in a very first lecture that pressure changes with depth. Okay, or height. So the deeper you go, the higher the pressure, and that's because the force above you increases. Now the question is there a relationship between these two, between the two concepts that we've learned so far? If pressure is related to depth, is pressure also related to speed? And in which case are we able to relate, therefore, the change in depth to the change in speed of the fluid? Of course, the answer is yes, because otherwise we will end our lecture and we'll all go home. Yes, pressure is related to the speed via Bernoulli's equation. So Bernoulli said that the pressure of a fluid will change if the height or elevation changes, and that's what we've learned before. the deeper you go, the higher the pressure. But Bernoulli says that the pressure will also change when the speed of the fluid changes. Okay. And Bernoulli's equation, well, this sentence is written down in mathematical form via this equation here. So you have pressure P, speed V, and elevation or height Y. So, so this equation, Bernoulli's equation, relates the pressure, the speed, and the heights on one point of the pipe to the pressure, the speed, and the elevation at another point of the pipe. So let's just define terms. P1, that refers to gauge pressure at one point. Yeah. V, that's speed or velocity. Yeah, it's really a speed. And Y is the height or elevation. So you are looking at 2 points along the pipe. So say this is point 1 and this is point 2. In this scenario here, the height changed between point 1 and point 2, the 2 points that you're looking at. In this scenario on the left, you can look at this as point 1 and some point here as point 2. So in this scenario on the left, or rather scenario on the left, at point 1 there is a wider cross-sectional area, and at point 2 there is a narrower cross-sectional area. So Bernoulli's equation compares the pressure, the speeds, and the elevation at one point, whether at this point here or at this point, compares the pressure, speed, and elevation at one point to the pressure, speed, and elevation at another point. Right. And I just need to point out that pressure here is measured as gauge pressures, because in Bernoulli's equation, we are looking at pressure as a function of height or depth. Okay, so yeah, seemingly complicated equation, but yeah, seemingly long equation, but all it does is it's just comparing the pressure, speed, and elevation at one point of the pipe to the pressure, speed, and elevation at another point of the pipe. And we'll analyze Bernoulli's equation as we go on in this lecture. Right? Okay, but before we continue, some points to note. Bernoulli's equation is only valid for when the fluid is ideal. Okay? And the scope of this course really just considers an ideal fluid, meaning the fluid's density is constant. So we say that the fluid is incompressible if its density doesn't change. We assume that it's the same fluid flowing through the pipe and its density is the same. The fluid, we also assume that there's no friction inside the fluid, so the water molecules, they don't encounter friction amongst themselves, in which case that we say that the fluid is non-viscous. Bernoulli's equation is also valid when the flow is laminar, meaning the speed can change, but it's not too fast so as to cause turbulent flow. Okay? And since the flow is laminar, if you place a disc where the fluid is flowing, the disc will move along, but it will not rotate. So those are just assumptions for which Bernoulli's equation is valid. And the biggest thing is, since we are assuming that there's no friction, then there's nothing dissipating energy, and therefore Bernoulli's equation is a statement of the conservation of energy for fluids. And that's why, and as a result of conservation of energy, we are able to relate, the left-hand side should be equal to the right-hand side because there's no loss of energy, even if the fluids goes through a height, or even if the fluid flows faster or slower. All right. Okay, so let's look at an example of how we apply that long equation. So in this scenario, water circulates throughout a house, which has a basement and a second floor. So water is pumped at a speed of 5 meters per second here in the basement, okay, at this one here. And we can use that as the reference height, y is equal to 0. The pipe at the basement where the fluid is initially pumped through at is 6 centimeters in diameter. Okay, and then it has a gauge. The fluids at the basement is pumped at a gauge pressure of 75 kilopascals. Right, on the second floor, the pipe narrows to a diameter of 4 centimeters, and the second floor is elevated by a height of 2 meters relative to the basement. Right, what we want to find is the flow speed, or how fast water is flowing at the second floor, and also we want to find the gauge pressure at that higher elevation. All right, let's do the speed first, because for speed, so let's analyze this conceptually. So at the basement, you have a wider pipe. At the second floor, you have a narrower pipe. So right away, we know from continuity equation, the speed will change, right? Because wider pipe, you have slower fluid flow, narrower pipe, the fluid flow should be faster at the second floor where the pipe is narrower. So we know that. The elevation changed, and therefore the pressure should change according to what we learned, that the pressure depends on the depth or the height. Okay, so let's do the speed first, because that seems to be simpler. Just by using continuity equation, we can determine the new speed because we are able to determine the new area. So from continuity equation, we want to find V2. That's V2 at the second floor. So V2 is equal to V1A1 over A2. Right, I can expand this as V2 is equal, so A1 is pi R1 squared, A2 is pi R2 squared, right? So pi sort of cancels out, and then we just need the ratios of the radii. Okay, so the initial speed, that's 5 meters, okay, times R1 squared. So diameter is given 0.06 centimeters, therefore R1 is 0.03 meters squared. Don't forget. I'll just remove the units here for simplicity. Right, so don't forget to square your radius divided by radius of the pipe. In the higher elevation, its diameter is 4 centimeters or 0.04 meters. Therefore, the radius is 0.02 meters. Don't forget to square the radius as well. Good. All right. Okay. Straightforward enough. So the next question is, so we've determined the flow speed. We want to find the gauge pressure. So we said that at the basement, this is point A. Okay. And at the second floor, that is point 1. So, so the subscripts in Bernoulli's equation, they all refer to the point. So that means P1, pressure at point 1 at the basement, that's given, 75 kilopascals or 75,000 pascals. V1, that's also given, 5 meters per second. Y1, that's the elevation at point 1, and we said that's the basement. We can say that that's the zero reference elevation. All right. Okay. Now for the second floor, P2, that's what we want to find. V2, we've calculated that from the previous question, 11.25 meters per second. And the elevation is given. The second floor is 2 meters relative to the basement. Okay. Right, so in Bernoulli's equation, this curly P, this is rho. That's the density. Water is flowing through the pipe. Density of water, 1,000 kilograms per cubic meters. Cool. All right, so we sort of have everything that we need in Bernoulli's equation except for P2. P2 is what we want to find. Right, so we rearrange Bernoulli's equation to isolate P2. So the left-hand side sort of stays the same because we're not changing anything. On the left-hand side, rho G Y1. Okay, and then get rid of these two terms to isolate P2. That will be minus 1/2 rho V2 squared minus rho G Y2. Right, so you can leave your equation as this and you can substitute all the numbers because you have everything. I don't want to punch a lot of numbers in the calculator, so I can simplify this by combining terms. So if you notice, you have 1/2 rho in this term and 1/2 rho in this term as well. So you can combine those two terms, factor out 1/2 rho. And so you have V1 squared minus V2 squared. Just combining these two terms and factoring out what's common to them, which is 1/2 rho. Okay. And then notice that rho G also appears in these two terms. So you can also factor out rho G from those two terms. So you have rho G and you have Y1 minus Y2. So you can do that if you want, but essentially we can now substitute numbers. Yeah, and I can just let you substitute numbers. They're all here, 75,000, yeah, density, V1, V2. You should get a pressure of 4614 pascals. Or 4.6 kilopascals. Right, if you don't get that number, this is probably a bracketing issue. So make sure when you add terms, you bracket them. Okay, good. Any question about the solution, or is that relatively okay? Yeah. So using Bernoulli's equation, again, you're just comparing two terms. But Bernoulli's equation becomes interesting if we consider two cases, right? So the first case we'll consider is when the pressure is static, meaning there is no flow, but the elevation changes. So let's see how Bernoulli's equation can be simplified in this first case when there is no flow and elevation changes. No flow means that speed is equal to 0. So the fluid's not moving. V1 and V2 are therefore equal to 0. So these terms, these two terms, they're just equal to 0. And Bernoulli's equation reduces to this form. So you're only just comparing the pressure at one height to the pressure at another height. And the implication, because this is an equal sign, right? It's a balanced equation. So left-hand side should be equal to the right-hand side, which means that if the elevation Y2 increases, the pressure needs to decrease in order to maintain this constant number. Okay? And this is exactly what we learned in lecture 22 in the beginning of this topic, right? We learned that as the depth, as we go deeper, the pressure should increase, okay? And at a higher height or higher elevation, the pressure should decrease. So this is exactly what we learned before. And it's so then Bernoulli's equation is consistent to that. You can also write this as, P1 minus P2 is equal to rho G Y2 minus Y1, in which case you have delta P is equal to rho G delta Y. And this is exactly what we learned with gauge pressure. P is equal to rho GH. So it's, the case where there is no flow is exactly what we learned before, where pressure increases with depth, right? Okay, the second case is when you have flow but without elevation. So here you have your water flowing through a horizontal pipe. The area changes. Okay. So you have a change in cross-sectional area, and therefore you have a change in speed, but the elevation is the same. So in which case, Y1 is equal to Y2. There's no change in elevation, and therefore this rho G Y1 is equal to rho G Y2, in which case they cancel each other out, and Bernoulli's equation reduces to this form. It only compares the pressure at one point and the speeds at one point and at those 2 points. Okay. It's again a balanced equation. Left side should be equal to the right side, which implies that if the speed is large, if the speed increases, then the pressure needs to decrease in order to maintain this equal sign. Okay. So as we can see here in what we've just learned earlier in this lecture, if the area increases, you have low velocity, you can think of the water molecules, because they can move slowly, they have time to muck around because they're moving slower. And as they muck around, they bump the sides of the pipe or the container. And as they bump the sides, they exert pressure, they exert force. And the more force they exert on the sides, the higher the pressure is, right? Okay, so you can think of it this way. The slower the fluid flows, the more it can hit the sides of the pipe, and therefore the higher the pressure. Okay, in the narrower part where the fluid flows faster, the water molecules sort of need to move faster, so they don't have time to muck around and bump the sides or hit the sides of the pipe, and therefore there's not a lot of force being exerted on the sides of the pipe, and therefore you have lower pressure. Okay, so higher the speed, the lower the pressure, the lower the speed, the higher the pressure. And this special case of Bernoulli's equation is quite interesting because it has many interesting applications. So one of them is here. I have paper, and I want to raise this end of the paper higher. If I blow on the paper, do you think if I blow downwards on the paper, do you think this side will go down or rise up? Did you see it rise up? What if I blow with, harder? I blew harder, it rose up higher. Why? Right. Let's sort of. Yeah, good. Exactly. That's what's happening. So I blew air on here. So high speed, low pressure. Okay. So pressure here is lower than the pressure. So pressure above the paper becomes lower compared to the pressure underneath the paper because there's just still air underneath. So higher pressure underneath pushes towards the lower pressure above, and that's why the paper rises up. So I have here a reverse vacuum cleaner. It's a reverse vacuum cleaner because instead of sucking air, it blows air. So it's a reverse vacuum cleaner. It's not sucking air. It's actually blowing air. So maybe you don't believe me. It is blowing air, but how come the ball is not blown away? Like it's blowing air away. So where the air is being blown, so you have high speed air here. High speed air produces a low pressure column. And the surrounding air is quite still, or they're moving slower. So high pressure where air is still, low pressure where air is moving faster. So you have the high pressure confining the low pressure column. And the ball is not blown away. Surprisingly, even if I tilt this thing, you still have high pressure column here, low pressure column being confined by the high pressure. Right. Okay. It's also the same thing if you've been to the train stations. Have you noticed the yellow lines near the train tracks? Why are the lines there? And why are you not supposed to stand beyond the yellow line? Watch this video. What could happen if you're standing beyond the yellow line? So watch that baby carrier. Right, thankfully there's no child there, but you just imagine, right? Okay. So right, so you have the train here is moving very fast. So you have high speed, low pressure, still air, slow speed, high pressure. Okay. High pressure pushes onto the low pressure. And so, yes, take that yellow line seriously because yeah, the change in pressure can be quite dramatic. So it's also the same case when you're overtaking, especially if you're overtaking a truck. You're passing a truck. Be careful and provide enough space, because if you're passing and you're if you don't provide sufficient space, then you create this very fast moving air column between these two vehicles. Low pressure, so high speed, low pressure. Of course, here the air is moving slower, so you have high pressure, and that causes some accidents. Right? Similar concept with ships. You'd think that the ocean is so wide. How come ships, collide? It's because if two ships are, say, moving this way, and if there's a strong wind that blows between them, okay, strong wind creates low pressure and causes the ships to collide. The next time, yeah, and again, also when you pass a cyclist, that's why you have to pass with sufficient distance, because you can really suck the cyclist into your car. Okay. The next time you watch the weather, the news, and they talk about the weather, and they're saying, we'll have sunny skies, there's a high pressure. We have high pressure, so we'll have sunny weekends. High pressure means slow speed. Low pressure area means cyclone or typhoon, because you have fast moving wind. Okay. Cool. So yeah, so that case of Bernoulli's equation, that case of Bernoulli's principle relating pressure and speeds is quite an interesting thing. Cool. So just to wrap up and relate everything together. So you have here a pipe with varying radii, and of course then cross-sectional area. So you have pipe A, B, C, and D. The radius of the pipes are such that C is widest, followed by A. And B and D, they have the same radius and they are the narrowest. So we assume that the height is constant, and the fluid flows, it's the same fluid with constant density. So relate the flow rate, cross-sectional area, speeds, and pressure in each of the pipes. So flow rate, what can we say about the flow rate? It's the volume, or how much fluid is passing through each of these pipes. Should be the same, right? Because it's the same fluid. Same 1 liter coming in should be 1 liter coming out. Cross-sectional area, well, we are given the relationship for the radii of each pipe. So cross-sectional area, straightforward, it follows the relationship of the radius. Speed, okay, what can you say about the speed of the fluids in each section? Right, which pipe should have the slowest speed? C, right? Slowest and fastest, B and D. B and D, of course, they're the same. And pressure, which pipe will have the lowest pressure? Pressure, Bernoulli's equation says fast speed, low pressure. Cool. Right, any question about Bernoulli's equation, continuity equation, fluids in general, or anything else? Cool. Yeah.
This is the same way that most scientific things work. This is already like stuff flowing through the pipe as well as the low pressure, so things need to get sucked out.
Yeah. Yeah. It's the same concept. Cool. Good. All right. So that ends our discussion on fluids, fluid statics, and dynamics. You'll have the workshop tomorrow where we'll look at all of what we've learned. So have a good day, everyone, and I'll see you in tomorrow's workshop.